Okay. So let's talk about what we would do right now if we were to try and differentiate something like that. Well, right now, all you have to do is, multiply it by itself because you're squaring it, and that would give you that. And then I think that'd be pretty easy to differentiate using the rules you already know, and you can get the derivative pretty easily that way, right? However, if the function was raised to a larger power, say 6, for example, would you want to expand that 6 times and have a 20-term polynomial to differentiate? No, it's too much work, so there is a better way. And so basically the new rule to handle that will be called the chain rule. And again, we're going to use a chain rule in a minute. And so basically you're going to use the chain rule to take the derivative when you have a composition of functions. And again, you remember from algebra that a composition is simply when you have a function inside of another function, like that. And so in that case, the inside function would be 3x plus 5, and if you call that u, for example, then you can think of the outside function as being u to the 6th power. Does that make sense? Okay? Okay, so here's how the chain rule works. And once again, I'm going to say that you use the chain rule when you have to take the derivative of a composition of functions. Okay, so if you have f of g of x, okay, where g is the inside function and f is the outside function, it's simple. What you do is you take the derivative of the outside function, which will be f prime, and then you put the inside function back in exactly the way it was, and then you finish the chain rule by multiplying by the derivative of the inside. Okay? So again, here it is, in words. You take the derivative of the outside function while putting the inside function back in exactly the way it was, and then you multiply all of that by the derivative of the inside function. Okay? Okay. Now there's other ways to write the chain rule. You might see it written this way in other textbooks. If y is the outside function and u is the inside function, then take the derivative. You simply take the derivative of the outside function with respect to u, and then you multiply that by the derivative of the inside function with respect to x. So that's another way you can write it. And when you write it that way, you can kind of see how it works out, because the du's technically would cancel, wouldn't they? Leaving you with what? dy over dx. So, I mean, that's just another way to show how it works. Does that make sense? Okay? Here's probably an easier way. If you think of the function as being f of u, in other words, f is the outside function, u is the inside function, then you simply take the derivative of the outside function, which would be f prime, put the u back inside the way it was, and then multiply all that by the derivative of the inside, which would be u prime. Is this making sense? All right, so it sounds complicated, but after we've done a couple examples, you see it's not too bad. Once again, as in past sections, the hard part is the what? Yeah, the algebra. That's the hard part. The calculus part is the easy part. Okay? So if I want to take the derivative of that function, clearly that is a composition, right? Agreed? Okay, the inside function is what? The inside function is, you can say, is u equals 3x squared plus 5. So 3x squared plus 5 is the inside. And at that point, if you call that u, then the outside function would be u to the 8th. Does that make sense? Okay, and so if the outside function is u to the 8th, what's the derivative of the outside? Well, 8u to the 7th, right? If the inside function is 3x squared plus 5, then what would be the derivative of the inside function? Well, it would be 6x. Okay? So at this point, we can use the chain rule as follows. To take the derivative y prime, you take the derivative of the outside function, which is 8u to the 7th, right? And then you multiply all that by the derivative of the inside function, which is 6x. Okay, and again, don't forget, you're supposed to put the u, which is the inside, back in exactly the way it was. So wasn't it 3x squared plus 5 at the beginning? So put that back in. And then at that point, if there's any simplifying you can do, go ahead and do that. Well, the only thing I can really do is take the 6x and multiply by that 8, giving me that as the final answer. Okay? Any questions? Okay, let's go to another example. Again, isn't this a composition? Yes? Okay? And by the way, for derivative purposes, I'm going to rewrite it like that. Okay, same thing. That's just using algebra 1. And so again, the outside function at that point would be u to the half. And if you take the derivative of that outside function, you get 1/2 u to the negative half, which simplifies to that. Okay? And then the inside function would be x squared plus 1. And we all know the derivative of that is just 2x. And so we're ready to use a chain rule. So again, we take the derivative of the outside function, which is this. And then notice what I did. I put the inside back in exactly the way it was. So I put the x squared plus 1 back inside there. And then you finish the chain rule by multiplying by the derivative of the inside, which is just 2x. And then at that point, the only obvious simplifying we can do is cancel the 2's, right? So if we cancel the 2's, we end up with this as our final derivative. Okay? Any questions? Okay. Now, I'll tell you right now, you don't have to write all those steps. I'm just trying to get you used to it. Eventually, you can go right from, the first step to, one of these later steps and without actually having to write down what the outside and the inside is. You can do all that in your head. Okay? Okay, so here we go. Now, let's look at something like this. Okay, we have some options actually here. We could actually leave it the way it is and then just use the quotient rule, correct? And that would work just fine. Or you can use algebra 1 and rewrite it like that. Everybody agree that that's the same thing using algebra 1? And at that point it becomes a composition, doesn't it, if you write it like that? And so if you're going to change it to that first, at that point you're going to have to use the chain rule. Okay, so let's just do it that way. Ready? So what I'm going to do is I'm going to take the derivative of the outside. So what I did is I brought down the exponent, which is -1, multiply it out front, and then subtracted 1 from the exponent. And at that point, I put the inside back in exactly the way it was, right? And then you finish the chain rule by multiplying all that by the derivative of the inside, which I think you'll all agree is -8x. Does that make sense, guys? Okay, and then at that point, just simplify, the negatives cancel, and you should put this in the denominator so you can make it a positive exponent. And that's it right there. Okay, so again, never leave a fractional exponent in your answer. Never leave a negative exponent in your answer. And also do any other obvious simplifying that you need to do. Okay? Let's look at example 4. Let me use a darker pen here. Okay, so here's the function. All right, let's talk about it before we start. You actually have a couple options here. If you left it the way it is, you'd have to use the quotient rule, right? And then along the way, when the time came to take the derivative of that, wouldn't you have to use the chain rule on that along the way? Okay? Okay, so that's one way you could do it. Or if you wanted, you can move this up to the top and make that a -3, and at that point you would use the product rule, right? And again, along the way you would still need to use the chain rule. Correct? Okay? I suggest you leave it like this though. Okay, but I did want to talk about your options. Okay, so here we go. Again, write kind of small so you can fit it in your notes there because it is going to be a lot of steps. Okay. So because it's a quotient the way it is, I have no choice but to use the quotient rule. Ready? So if you remember, the quotient rule says you take the derivative of the first function, which is that, times the second function, which is that, and then minus in brackets the first function, which is that, and now times the derivative of the second function, which is a composition, isn't it? And so I have to use a chain rule when I take the derivative of this right now. Are you ready? So how do you take the derivative of that using the chain rule? Well, you bring down the exponent, subtract 1 from the exponent, right? That's the derivative of the outside. Everybody agree? Put the inside back in exactly the way it was. And then don't forget to finish the chain rule by multiplying by the derivative of the inside. That's where you're going to make your mistake if you're not careful. So what's the derivative of the inside, guys? 6x, that's right. Okay. All right, and then don't forget, all over the second one squared to finish the quotient rule, correct? Okay? All right, now you got a mess to clean up, right? Huge mess. Okay, so here's what I'm going to do. I'm going to leave that alone for right now. And then here, what I'm going to do is I'm going to multiply that, and that together, and that gives me, let's see, negative 90x squared, right? But then with that minus, it turns into a plus. So I get plus 90x squared, and then I still have this. And then all over, when you have a power to a power, you multiply those powers. Okay, now at this point, there could be some more simplifying you can do. Okay, but I'll wait for you to catch up. Okay, so at this point, what you want to do is you want to look at it on top as being this whole term plus this whole term. And then at that point, start looking for stuff you can pull out. What can you pull out of both of those terms? Okay, you can pull out a 5, because 5 goes into 5 and 90. Right? And by the way, when the first term's a negative, you should also pull out a negative along with anything else you can pull out. So I'm definitely going to pull out a negative and a 5. And then if you look at these, don't both terms have 3x squared plus 2 to at least the second power? And so I'm going to pull that out as well. And then just write what's left over in brackets. So if I pull all of this out of that box, I'm left with a 3x squared plus 2. And you got to, when you pull a negative out, this turns into a what? A minus, right? And when I pull all of this out of here, I'm left with what? An 18x squared. Is that it, right? Is that it? Okay. And so at this point, you want to simplify what's inside the brackets. I can definitely combine these into a minus 15x squared, right? Plus 2. Okay. And then at that point, clearly, I can cancel some of these 3x squareds plus 2, right? I can cancel both of those with 2 of those, leaving you with a 4 there, correct? Okay? And so this is my final simplified derivative then. Okay, any questions? Okay, so there we have to use a chain rule along with the quotient rule. You could distribute the 5, but this is considered simplified because it's factored. Pull out the 5. If I put the 5 back in, then it wouldn't be factored. So try and factor your answer. Okay? Okay. All right, now let's go down to example 5 here. All right, so this one's going to be a lot simpler, obviously, but take a look at it. I do have a composition, don't I? Don't I, guys? Yes? Because the outside function is sine, and the inside function is 2x. Everybody agree with that, that this is a composition, so I must use the chain rule when I take the derivative? Okay, so here it goes. Once again, chain rule always works the same way. You start by taking the derivative of the outside. So what's the derivative of sine? The derivative of sine is just cosine. So that's the derivative of the outside function. And then you're supposed to put the inside function back in exactly the way it is. And then you multiply all that. And so I'm putting it in brackets. You multiply all that by the derivative of the inside, which is what? 2. Okay, the reason I put the brackets there is to make sure you understand that you're multiplying this by the whole thing, not by the inside. Because if I didn't put those brackets there, you might take the 2 and multiply by the 2x, which would give you cosine of 4x, and that's incorrect. So do you see why I put the brackets there? Okay. All right, so do you agree then this is correct? And so because you're multiplying the whole thing by the 2, to make that clear, I want you to put the 2 out front. And then just get rid of all those brackets and parentheses and just leave it like that. Okay, so that's your final answer there. Good? Okay. Now let's look at example 6. Okay, so we've got f of x equals cosine of 5x squared. And again, if I were you, I would think of it and actually rewrite it like this, so there's no confusion on what's the inside and the outside. Okay, so this is the way, you should rewrite it before you start taking the derivative. Okay, so at this point, again, I'm ready to use the chain rule to take the derivative, and so I start by taking the derivative of the outside. What's the derivative of cosine? Negative sine, that's correct. Okay, so you start by taking the derivative of the outside, which is negative sine, then don't forget to put the inside back in the way it was, and then you finish the chain rule by multiplying all that by the derivative of the inside, which is 10x, that's right. Okay, and again, you want to put that 10x out front so it doesn't end up being multiplied by the angle. That would be incorrect if you multiplied the 10x and the 5x squared. That would be incorrect because it's the 10x times the whole trig function. And so this is the way I want you to write the answer without all those brackets and parentheses. Okay? Good? Okay. Okay, and so looking at example 7, if you look at it, notice what I did. I took what I gave you and I actually rewrote it with a bunch of parentheses and brackets just to make it very clear what's going on. And again, as I said last time, when the exponent is between the trig function and the angle, what that means is it's the whole trig function that's being raised to the power. So that's why I wrote the whole trig function inside brackets and I put the 4 on the outside to make that more clear. Got it? And then I also put parentheses around the 5x squared to make sure that stays inside of the sign. Okay, so I'm just rewriting it so I can see it more clearly. I didn't do anything as far as the derivative goes. Is that clear? Okay, so if you look at it like that, then the outside function would be u to the 4th. The inside function would be the sine, right? And then the inside of the inside would be the 5x squared. Does everybody see that? So this time you got an inside function and then an inside of an inside function. Right? And so this is a composition of 3 different functions, isn't it? And so here's how the chain rule would work then. To take the derivative, you would take the derivative of the outside by just bringing down the 4 and subtracting 1 from the 4. So that's the derivative of the outside. And then you would put the inside back in there. Okay, so the inside was sine sine of 5x squared, right? Okay. And then you would take the derivative of the inside by taking the derivative of sine, and you should all know that the derivative of sine is just cosine. And at that point, you would put that inside function back in, which was 5x squared. And then at that point, you would take the derivative of the inside, and so the derivative of 5x squared would give you 10x. Okay, and then so the only thing you could do there at the end is multiply that 10x by the 4 to give you 40x out front. And so that's your final derivative right there. Okay? All right, now let me back up a minute because you probably have a question. If I go back to example 5, for example, you're probably saying, well, why didn't I keep going on the inside here? Well, you could. And so if I took the derivative of the inside here, what would be the derivative of the x? What would be the derivative of x? 1. And so would that really change the answer? No. So if you're wondering why I didn't keep doing it on something like this, well, I could, but eventually I got to the inside where the inside of the inside was x, and then the derivative of x is just 1. So that's at that point you're done. Does that make sense? Yes? Okay. All right, so let's look at example 8. Okay, and I'll do this on a separate piece of paper. Okay, so I have f of x equals sine cubed of x. And again, if I give you something written like this where the exponent is between the trig function and the angle, you should think of it and even rewrite it as this. Okay, so now, at this point, you can see clearly what the outside and the inside function is, right? The outside function is something cubed, right? And the inside function is sine x. With me? With me? Okay. And so, to take the derivative, you start by taking the derivative of the outside by bringing down the exponent and subtracting 1 from the exponent. And at that point, don't forget to put the inside back in exactly the way it was. And now you finish the chain rule by multiplying by the derivative of the inside. And so what's the derivative of sine? Cosine. Okay, so at this point, I would bring the cosine out front like that. It really doesn't matter the order. But I would rewrite this as sine squared x. Okay? Any questions? Getting the hang of it? Okay. Okay. Okay, so you guys, here are a couple more derivative formulas. We already know that the derivative of e to the x is just e to the x, right? Now, if we apply the rule, the chain rule, on something like this, okay, where the exponent is something more complicated than just a plain old variable, well, then again, you would take the derivative of the outside times the derivative of the inside like we always do. And so in this case, the derivative of e to the u would be the derivative of the outside, which is just e to the u, and then times the derivative of the inside, which would be, u prime. And so it follows the same pattern, except that in this case, if the exponent is something more complicated than just x, it becomes a composition, where you would need to do something like this by taking the derivative of the inside as well and multiply it at the end. Okay? Make sense, guys? Okay. Now, let's look at something like this. What if the base is not e? What if it's some other number a? Well, it starts out the same, right? Derivative a to the u is a to the u, and then by the chain rule, you multiply by the derivative of the inside. But there's an extra factor in here that you have to multiply by the natural log of a. Okay, and if you're wondering why I didn't do that over here, well, let me explain. I could, okay, because if I did that, I would have what out front? I would have a ln of what? E out front. But what is ln of E out front? 1. Isn't ln of E just 1? So it's there, it's just, it turns into 1, so you really don't need it on this formula. So what I'm saying is these are basically the same formula, aren't they? Yes? Okay? All right. Okay, so let's look at example 9. Okay, we've got f of x equal e to the sine x. And so clearly that's a composition, so I'm going to have to use a chain rule. So the derivative of e to the u is e to the u times the derivative of u, right? So derivative of the outside times the derivative of the inside, right? It's just a chain rule. So, so what I do is I take derivative of this, which is in the form e to the u. So the derivative of e to the u is just e to the u. And then times the derivative of the inside. And so what's the derivative of the inside function sine? Well, yeah, the derivative of sine is just cosine. Okay, and that's it. So if you want, you can rewrite it like this. Same thing, right? No big deal. Any questions? Good? Okay. All right, let's look at example 10. Okay, now be careful here. I don't think you want to leave that the way it is, because if you do, when it comes time to take the derivative of that, you're going to have to use the quotient rule, right? You don't want to do that. So what I'm going to do is I'm going to rewrite it using algebra 1. Isn't that the same thing as negative 1 x to the negative 1? Or just, you know, e to the negative x to the negative 1? Same thing, right? So all what I'm going to do is I'm going to rewrite it using algebra 1. Okay, I haven't done any calculus yet. Okay, there it is. Okay, and so at this point, I'm going to go ahead and take the derivative. So here it goes. You start by taking the derivative of the outside. So the derivative of something in the form e to the u is just e to the u, and now times the derivative of u. In other words, times the derivative of the inside. And so to take the derivative of that right there, instead I'm going to take the derivative of that. Okay? And so to take the derivative of that, I'm going to bring down the negative 1, multiply it out front, giving me a positive 1, and then subtract 1 from the exponent. Okay? Got it? And then at that point, simplify it. I'm going to move this to the denominator so I can make it a positive exponent. And so at that point, I have that. And if you want, you can also move that to the denominator so you can make that into a positive exponent. And so at that point, I would have this. Okay, so either way is fine. Any questions on that? Okay. I know this is a little bit grueling, but this is just one of those days where I have to do a ton of examples to prepare you guys to do the homework. Okay? If I don't do this variety of examples, you're not going to be able to handle everything that's going to show up in the future. Okay? As you can tell, every example I've done is different than the last. Hasn't it been? Yes, and that's just the way it goes sometimes. Okay, so I apologize, but let me keep going here. Example 11. Okay, and so I think you'll understand, or agree, I should say, that this fits that second rule I just had up there, this one,
Yes.
right? Okay, where you have a base other than e, right? So if you have a base of 2, you're going to have to follow this rule, right? So just remember, there are 3 pieces to the derivative rule here, aren't there? Yes? Okay, so here's what you want to do. What I would do is always do the middle piece first, because that's the easiest one. Okay, so when you take the derivative, you start by this is in the form a to the u, right? And so the derivative of a to the u is a to the u in the middle, so just recopy it, right? And then the chain rule says you have to multiply that by the derivative of the inside. And so what's the derivative of 4x to the 5th? 20x to the 4th. And don't forget that third piece out front, it's the ln of a. In other words, you take the natural log of the base, which would be ln of 2. Everybody agree with that? Yes? Okay? And so there's really not a whole lot you can do here. However, if you want to avoid having to have all those parentheses, you could probably change the order around in your answer. I would probably write it like this. But it's up to you. I mean, by writing the ln of 2 at the end, I don't need parentheses. Okay? Does that make sense? But it doesn't really matter what order it's in. Any questions? Okay, so get example 12. Okay, so we have y equals 5 raised to the cosine of pi x. And so if I were you, what I would do is I would add in the parentheses there, just to emphasize that the pi x is the inside of the cosine function, correct? Okay, so again, do you agree it fits this rule right here, where you got the base other than e? Yes, and so aren't you going to have to use this 3-part formula? Yes? Okay, so here it goes. So you start by taking the derivative of, that, which is the a to the u. So the derivative of a to the u is a to the u in the middle. So just recopy it the way it is. And then the next thing I would do is multiply that by the derivative of the inside. And when you go to take the derivative of the inside, you run into another composition, don't you? And so you have to take the derivative of cosine, which is negative sine. Okay? So you take the derivative of the outside, put the inside function back in the way it is. Right? And then you multiply all that by the derivative of the inside of that. So what's the derivative of pi x? Pi. Okay? Okay. So again, let me repeat what I did so far. The derivative of u is a to the u, and then times the derivative of u, which is the derivative of the inside. So I took the derivative of cosine, which is negative sine. And then like I always do with the chain rule, I put the inside back in exactly the way it was. And then I finish that chain rule by multiplying by the derivative of the inside. So the derivative of the inside, in other words, the derivative of pi x is pi. And then don't forget, what's the third piece to the formula? Out front, you're supposed to have what? ln of a, which in this case is natural log of 5. Okay? And so, and I'll be careful there. Okay, what I'm going to do is I'm going to pull this pi out front with that, and I'm going to pull the negative out front as well. So I would probably just write the answer like this. Whoops, sorry. Let me just rewrite it, sorry. Really doesn't matter where you put that, but anyway. Okay, so by writing it something like that, you really don't need as many parentheses. Oh, I'm sorry. Yep, I lost my negative. That should be out front. Thank you. Okay? Is that good? Does that make sense, guys? So again, it's just a matter of remembering the 3-part formula. Okay? Okay, so let's look at example 13. Okay, this time we have y equals e raised to the secant of 3 theta. Okay, so clearly this is in the form e to the u, right? So to take the derivative of something in the form e to the u, it's e to the u. So just copy that exactly the way it is. And now I need to multiply all that by the derivative of u. In other words, I need to multiply by the derivative of the inside, which is this. The thing is, when you go to take the derivative of that, it's also a composition itself, isn't it? So don't you have to use a chain rule on that? And so the derivative of secant is secant tangent. And again, you're supposed to put the inside back in exactly the way it is. Okay? And then you multiply all that by the derivative of the inside. Well, what's the derivative of 3 theta? Well, that's no different than taking the derivative of 3x, is it? So what's the derivative of 3 theta? 3. Okay? And so again, just so things don't get mixed up inside the e function, I'm going to rewrite it like this. Oops, sorry. Okay, so again, I know it's different, but if you follow the rules, it's really not that bad. You just got to make sure you keep taking the derivative until, there's no more derivatives to be taken. Right? Got it? Okay. Okay, cruising right along. Let's look at 14. This one is definitely different again. So let's look at that one. Okay, so I'm going to switch things up a little bit on you and look at something like this. Example 14. Okay, the first thing I'm going to do is rewrite it like this for derivative purposes. Okay? Everybody agree I can rewrite it like that? Using Algebra 1? Okay, now again, I have a composition, right? And so I'm going to have to use a chain rule, yes? Okay, so here it goes. Okay, so I start by taking the derivative of the outside function. Well, the outside function is clearly tangent. And so what's the derivative of tangent? The derivative of tangent, if you remember from last time, is secant squared. And so after you take the derivative of the outside, you're supposed to put the inside back in exactly the way it was. Okay? And then multiply all that by the derivative of the inside. Now when I go to take the derivative of the inside, I'm taking the derivative of that or that, in other words, aren't I? And that is also a composition. So I'm going to have to use the chain rule on that by bringing down the exponent, subtract 1 from the exponent, put the inside back in exactly the way it was, and then finish that by multiplying by the derivative of that inside. And so the derivative of 1 minus 2x is negative 2. And so at this point, obviously that and that cancel, right? And to make this a positive exponent, I'm going to move it to the denominator, right? And then I'm going to change it to a square root at that point, right? After I move it to the denominator, I'm going to change it to a square root in the denominator, right? And so after doing all that, this is what I end up with. And please don't tell me that you can cancel the square roots, because this one is tied up inside the secant, isn't it? So you cannot cancel those. That's as far as you can go. Any questions? So again, I think that, this is, the best way to learn this stuff is just to see a ton of different examples so that you're prepared for just about anything. Okay? All right, I'm getting there, guys. We still have a lot of time, but I'm getting there. All right, now this one is actually very similar to one I saw in a previous AP exam, okay, where they really make things complicated. And so let's look at example 15. Okay, so they're putting a little twist on it. Okay, but what I would do then before you start is to rewrite it as something like this. Okay, so can I rewrite it like that using just some algebra 1 manipulation, right? Agreed? Okay, so now it's clearly a composition. And so I'm going to start taking the derivative by taking the derivative of the outside. And so to take the derivative of the outside, I bring down the exponent and subtract 1 from the exponent, right? Which gives me that. And I put the inside back in exactly the way it was, which is cotangent of square root of x. Okay, so that's the derivative of the outside with the inside put back in. And now I got to go inside and take the derivative of that. And so what's the derivative of cotangent? Negative cosecant squared. Very good. And then don't forget to put its inside back in the way it was, which if you think about it was just that or that, right? And then I got to finish the chain rule by taking the derivative of the inside of the inside. And so now I got to go inside and take the derivative of that. And I think you'll all agree that that's just 1/2 x to the negative 1/2. Okay? And by the way, if you're wondering why I don't go inside again, I could. Well, once I go inside, what's the derivative of x? 1. So I could put a 1 out here, but was that going to change the derivative at that point? No. So I'm done. You see how I'm done at that point? Yes? Okay. All right, so now it's just a matter of cleaning this up and getting rid of those negative exponents and the fractional exponents. So if you think about it, this is going to have to go to the denominator, isn't it? To make it a positive exponent. And this is going to have to go to the denominator, isn't it? To give it a positive exponent. Yes? And at that point, I'm going to turn those half powers into square roots. Okay? So if you do all that, and by the way, this is going to be on the bottom, that's going to be on the bottom, right? Okay, so doing all that, I'm going to be real careful here. Hopefully I won't make any mistakes. This is what I end up with on top. And then on the bottom, the 2 and the 2 give me a 4. And I've got the square root of the cotangent of the square root of x. That was just from that moved to the bottom and then turned back into a square root. And then this goes in the bottom as well. Okay. And yeah, I mean, if you combine the square roots, if you did combine the square roots, which you don't need to, if you did combine them, it would actually look like this. Okay, so if you did combine those square roots in the denominator, it would be that, wouldn't it? Okay. I know these are pretty tricky and nasty, but you know, once you get used to it and you've done a bunch of them, it'll be actually not too bad. Okay, guys, hang in there. I would give you a break, but I don't want to mess up my recording. I apologize, guys. Whatever time we have left, I'll give you at the end. Okay? Okay, so example 16. The good news is we're on the last page finally. One and a half pages, sorry. Okay. Yeah, this is bad, I know. So here it goes. Use small writing, guys. Hang in there. Okay, so we've got this. Okay, so for derivative purposes, what I'm going to do is I'm going to rewrite it as this. Okay, so here it goes, guys. Ready? So clearly this is a product, right? So I'm going to have to use the product rule, right? But along the way, when I go to take the derivative of this or this, it's a composition, so I'm going to have to use a chain rule somewhere along the way as well, right? Everybody agree with me? Okay? So, here it goes. So first the product rule. I take the derivative of the first function, which is that, times the second function, which is that, plus the first function, which is that, and now times the derivative of the second function. And so when I go to take the derivative of this, which is the same thing as that, clearly I'm going to use the chain rule, right? By taking the derivative of the outside, which is that, right? Bring down the exponent, multiply it out front, and subtract 1 from the exponent. Put the inside back in exactly the way it was, and then don't forget to finish the chain rule by multiplying by the derivative of the inside, which is negative 2x. So again, the calculus is done. The rest of it is all going to be algebra, right? Okay. So first thing I'm going to do is cancel those. I can combine that, that, and that. And so I end up with this. The minus is going to change this to a minus. And then I've got x cubed, right? Times this. Okay. And then what I'm going to do at that point is be careful. To make that a positive exponent, I'm going to move it to the denominator. So I move that to the denominator, it becomes a positive half exponent, which I'm going to turn into a square root. Okay, and then again, you're going to see why real soon, like next week. Why I don't want to stop there. So what I want to do is I want to now get a common denominator. And so to get a common denominator, I'm going to multiply this by this. And once I do that, what happens is this. I'm going to get one big fraction now. You should all know when you multiply two square roots, the square roots go away, right? Square root of a times the square root of a is just a, isn't it? Yes? And so that turns into just that. And then minus the x cubed is there as well. And then obviously at this point you want to distribute the 2x. And then finally, the last thing you can do here is combine those into a minus 3x cubed. So I suppose if you wanted to, you could pull out an x in the numerator as well, couldn't you? But that doesn't allow me to do much more. Right? Okay, guys? All right, look at the next one. Again, if you want any of these sheets, I'll just leave them up here for you guys for later. Good? Okay. Example 17. Feels like example 117, but anyway. Okay. Here we go. Okay, what are we looking at? Big picture, guys. What are we looking at? We're looking at a product, right? So clearly we're going to have to use the product rule. But along the way, we've got some compositions that we're going to have to deal with the chain rule, aren't we? Yes? Okay, so here it goes. Everybody should be writing these down. Should be writing them down. Okay? Yeah, because this one's definitely different. Okay, again, I wouldn't be doing it otherwise. So I start the product rule by taking the derivative of the first function, which, by the way, is a composition, so that requires the chain rule. So I bring down the exponent, subtract 1 from the exponent, put the inside back in the way it was, and then finish the chain rule by multiplying by the derivative of the inside, which is 3x squared. So all of that is a derivative of the first function, correct? Right? And now times the second function, which is just this. And then plus the first function, which is just this. And now times the derivative of the second function. So now I'm about to take the derivative of that, which is a composition, so I'm going to have to use the chain rule on that. So I take the derivative of the outside by bringing down the 3 and subtracting 1 from the 3. Put the inside back in the way it was. And then finish this by multiplying by the derivative of the inside, which is 2x. Don't forget that 2x. That's the mistake you're going to make. You're going to be so caught up in everything else you're doing, you're going to forget to take the derivative of the inside there on that last piece. So be careful. Is that clear? Okay, now, again, it's one step of calculus and a bunch of algebra. So watch what I'm going to do. I have to look at it, again, as this whole term plus this whole term. And as I do that, what I'm going to do is I'm going to go ahead and simplify a little bit by multiplying those. And then over here I can multiply those, can I, to make it a little bit nicer? Okay, so at this point, I still want you to look at it as being this whole term plus this whole term. And so at that point, you can now look for stuff to pull out. What can I pull out? What do they both have in common? Well, what number goes into 6 and 15 evenly? A 3. So I'm definitely going to pull a 3 out. This has an x squared and that has an x, so I can pull a what? X out. Okay, looking at those, they both have that raised to at least the 4th power, don't they? So I'm going to pull all of that out. And then looking at those, they both have that to at least the 2nd power. So I'm going to pull that out. And then just write what's left over in brackets. Ready? Okay, so if I pull all of that out of here, I think you'll agree I'm left with a 5x and an x squared minus 5, right? But do you agree with that? And then bring down your plus. And then if I pull all of this out of here, I think you'll agree I'm left with a 2 and an x cubed plus 1. Right? Okay, so at this point, what I want to do is I'm going to distribute the 5x there and there. And then here I'm going to distribute the plus 2 here and here. And then, let's see, I can combine those x cubes. I'm getting there, guys. Okay, now look, sometimes you'll end up with a quadratic there that maybe factors further. Okay, so look for something here to factor further. But I don't think that's going to happen here. And so that's going to be as far as you can go. Trust me, if you're not able to, simplify and factor your derivative like this, you're not going to be able to apply derivatives in the next chapter. So yes, to answer your question before you ask it, you do have to go this far. Right? Plus, if this were a multiple choice question, you wouldn't be able to pick out the right answer without going this far. So yes, you're going to have to. Okay, guys? Okay? All right. All right, now 18 isn't as long. That's the good news. Okay, let's look at example 18. Okay, it is definitely a composition, right? Now, before I start, there was a homework problem on your last homework that some of you came in the seminar to ask about. It was something like this. That is not cosine theta times sine theta, is it? That is not a product. There's no theta there, is there? It's the cosine of sine. So this is not a product. This is actually a what? It's a composition, isn't it? Yeah. Do you understand the difference? Yes? Okay, so don't make that mistake into, by thinking that that's a product. That is not a product. That is a composition. Cosine is the outside function, sine is the inside function. Is that clear? Okay. So with that in mind, I think you have a better understanding of what you're faced with on something like this. So clearly the outside function is what? Sine. The inside function is cosine, and the inside of the inside function is tangent, and the inside of that is just plain old x. Okay? Stay with me. Heads up, please. Okay. So we start by taking the derivative of the outside, okay, by taking the derivative of sine. So you guys, what's the derivative of sine? Cosine? Yes? Now wait, now you got to stop right there and put the inside of that back in exactly the way it was. So I'm just going to recopy all of that. See what I did? All I did is took the derivative of the outside, which is cosine, and I'm supposed to put the inside back in, though exactly the way it was. You see how I did that? Okay, now you multiply that by the derivative of the inside. So now I go and take the derivative of cosine, which is what? Negative sine. And I put that inside back in exactly the way it was. Are you with me, guys? So I put that inside back in exactly the way it was, right? And now I take the derivative of the inside of that. So what's the derivative of tangent? Secant squared, and I put the x back in the way it was. And if I kept going, at the next step I would take the derivative of what? X, which is just what? 1, which doesn't change anything, does it, if I multiply by a 1? So you agree I'm done at this point? You see how I keep going on the inside of the inside? It's kind of like nesting dolls. You guys know what nesting dolls are, right? Where you open it up and then there's another one exactly like it inside, but it's smaller. Then you open that up and there's another inside, and you can keep going until there's no more insides. We'll kind of think of it like that, right? You know what I'm talking about? Okay. I actually think those things are kind of cool. But I had one a couple years ago with like little Detroit Lions players, but my son crushed it into about 1,000 pieces. Okay. Because it was real thin. It was real thin plastic it was made out of. But anyway. Okay. All right. Okay. The good news is it wasn't Barry Sanders. It was some other not very good player. So, okay. So anyway. So now I do got to clean this up. Now, you're not going to be able to avoid some of those parentheses in your answer. So some of those are going to have to stay. Okay? But definitely I would pull that negative and put it out front. Otherwise, it's going to look like a subtraction if I don't, which it's not. That is not a subtraction. That's some negative that you're multiplying by, right? So definitely pull the negative out front. I would probably pull the secant squared out front. And then, I don't know. I'd probably put this next. Again, the order really doesn't matter, and I'd probably put this last. Okay, but again, order really doesn't matter. By writing it like that, I think you can avoid some of those brackets and parentheses. Is that clear, guys? Okay, not going to get much harder than that. All right, now the good news is I'm not going to actually do anything with example 19. I'm just going to talk about what I would do. Okay, and then we'll finish up the last example. So, you've got a couple choices here, right? If you leave it the way it is, you're going to have to use the what? Chain rule, by bringing down the 9, multiplying it out front, subtracting 1 from the exponent, right? And then multiplying by the derivative of the inside, which would require what? When you go to take the derivative of the inside, you'd have to use the what? The quotient rule, right? So it would kind of look something like this. And then times the derivative of the inside using the quotient rule. So you'd have to do the quotient rule here. And then simplify. Does that make sense? Yes? That's one way you could do it, right? What's another way you could do it? Well, couldn't you rewrite it as that? raise the numerator to the 9th power over the denominator to the 9th power and then use the quotient rule? Yes? Now along the way you're still going to need the chain rule, right? Does that make sense? And actually a third option would be what? To bring this up to the top and make it a what? -9, and at that point you'd have to use the product rule. Again, I wouldn't recommend you do it that way because then you got a bunch of negative exponents in your answer, which turns real tricky at the end. So I wouldn't do it that way. I'd probably do, one of these two methods. Actually, I think method 1, believe it or not, would be the easiest. I think. But that's up to you. Okay? Got it? Okay, last page. Okay, this is actually not too bad. In fact, we'll just do A and call it a day. How's that? Fair enough? Because then B is the same thing, it's just a different number. Okay? Okay, so let's do example 20A. Here we go. Okay, so I want to find h prime of what, 2? Now, before I can find h prime of 2, I first have to find h prime of what? X, and then just stick the 2 in at the end, correct? So let's do it. Okay, so here's the given function. Okay, so I'm going to first find the derivative function, h prime of x, by looking at this as being a what? That's a what? What is that? It's a composition, isn't it? So don't I have to use a chain rule on that? And again, for about the 20th time today, how does the chain rule work? You take the derivative of the outside, which would be f prime, put the inside back in exactly the way it was, and then multiply all that by the derivative of the inside, which would be what? G prime of x. Okay? And so that's the derivative of that, and then minus, what's the derivative of that? 6x. Okay? Okay. So at this point, since that's h prime of x, and I want to find h prime of 2, I'm simply going to replace all the x's with a 2, and then go from there. So I'm going to put my 2 there. I'm going to put my 2 here. I'm going to put my 2 here. And I'm going to put my 2 there. Okay? All right, so here we go. What I want to do now is start picking out some of these values from the table. So go on the inside first. Looking at this table, what is g of 2, guys? Looking at this table here. What is g of 2? Well, g of 2 is just what? Everybody agree it's 3? So put a 3 there. Okay. And then, looking at your table, what is g prime of 2? Well, again, g prime of 2 is what? 1. So put a 1 there. And then this is obviously just 12. Everybody with me on that? Yes? Okay, and then from your table, now what is f prime of 3, guys? Again, looking at your table, what is f prime of 3? What is it? -4. And so finally then, at this point, I'm just going to finish it and get what? -4 minus 12, which is what? -16. And again, b is the same thing, it's just a different number. So you only have to do the last part of it, right? So just at this step, replace the 2 with a 3, and then just finish it. Does that make sense? Okay, I am done.